Hi, everyone. This is question 5. I just realized in the first four videos there was no sound, and I rebooted the program I used to make these movies, and it changed the defaults, and usually my sound was on, and I just realized that the sound wasn't on, so I'm really sorry about that. Um, if I have time, I'll go back and re-record them, but I'm going to move on and continue to create solution videos for you, and really sorry about the technical error. All right, so we are on question 5. 3 solid cylinders are supported by a hollow box. They each weigh 10 pounds. Let's make a note of that. And let's see, cylinders 2 and 3 contact the box. Cylinder 1 does not contact the box. System is in static equilibrium. And all the gray lines are at 30-degree increments in polar coordinates. And what we would like to solve in this problem are the reaction forces, or the normal forces that occur in the various bodies. So let's get into that. Of course, our free body is going to be the first step in just about every problem we work. So let's start with that. There are several free bodies that I could do, and you know what I'm going to do for this problem? So I've got a nice line of symmetry. So I am going to use that to my advantage on my tablet. So I'm going to lock in a line of symmetry. And what that means is I don't have to draw as much. So I can draw half of the circle here and it makes the full circle. Okay, and every now and then I'll write backwards, but we can live with that. Let's do a free body of this first sphere. So here is our normal force here. And that one we're going to label as 10 pounds. That's the weight. And then we have points of contact right there at point P. And I know that this is a concurrent force problem. So I've got 3 forces on the body. They all have to coincide at the center of that sphere. So let's go ahead and draw that. Maybe we do purple. Let's do a nice purple. There we go. Okay. And so we have a push force on both sides, and we can call that P. You know what I'm going to do actually? So I have that as point P. So I'm going to use N for normal force and then P for the point of application. And as we break these down into their component forces with a bounding box of something like this, I'm going to go just to the one over here. We know that that angle is at 30 degrees, just looking at the gray dashed lines in the diagram. So we know that this angle is 30 degrees. And we can use our memorized relationships for 30-60 triangles to go ahead and break those down. So we have a horizontal force and a vertical force. And like as we get that fleshed out, right, we're kind of ignoring the source there. And the long leg is equal to root 3 over 2 times n sub p, and the short leg is equal to n sub p divided by 2. Okay, as you can see, I'm doing a little bit of mirror image writing, but that's okay, you get the idea. All right, and we can very quickly solve this. So we could use those components that I set up, but as long as we know the ratios between them, and what I'm talking about here is that in a 30-60 triangle, if this is a 30-60 triangle, then the short leg is equal to the length of the long leg times the square root of 3. Okay, and that's because if it's a unit triangle, so this length is 1, and then the cosine of 30 degrees is root 3 over 2. The sine of 30 degrees is 1 over 2. So to go from here to here, all I have to do is multiply by square root of 3. So here's what I'm going to do. I'm going to use that symmetry to my advantage. And turn my symmetry line back on. Just kind of cover these up a little bit. And here's what I want to do with it. So vertical force equilibrium, I need 5 pounds for those two vertical forces to match up with the 10. And then my horizontal force here is just square root of 3 times 5 pounds. Okay, so we've got that free body in static equilibrium. And so if someone asked us for what is N sub P, can't remember if that's in the problem statement or not, then what we could do is use those ratios and say that N sub P is to the unit hypotenuse of a 30-60 triangle as the short leg 5 pounds is to 1/2, and deduce that N sub P is 10 pounds, which is twice the magnitude of the short leg. Okay, so we know that N sub P is equal to 10 pounds. And at this point, we're going to move to a different free body diagram. And I'm going to clean my marks up just a little bit so I can turn these on and off at will. Okay, so we're going to put all those together. Okay, so there's a free body diagram. And just to keep track of it, I'm just going to move it over here. I'm going to move it here. And I can always move it back in place if I want to do so, but let's just kind of get it out of the way a little bit, maybe up there. Okay. Let's start a new layer for another free body diagram. So let's go look at this sphere. And I'll turn the symmetry on, so I'll create two identical mirror image free bodies here. So I need to outline the body, and I need forces. So I need the body force. So we know that's 10 pounds. We need a normal force at Q. It needs to be perpendicular to the surface, so it has to go that way. We need a normal force at M. It has to be perpendicular to the surface, so it has to go that way. And we're looking at the surface that's not there, by the way, right? So I need lines that are perpendicular to the surfaces that have been moved away, taken out of the diagram. And so I'll call this one N sub Q. This one is N sub M. And then at P, I just need to put in a mirror image of the forces we solved for. Not a mirror image, but we need to put in the Newton's third law pairs of the forces that we just solved for. So what I'm going to do is I'm going to line this up. Okay, so I'm going to go from here to here. I'm just going to draw this yellow construction line temporarily. And I'm going to take that original free body and we're just going to put it on that line of action right there. Okay, and I'm going to take this background and really just fade it out even more so we can focus on the free bodies. Okay, that yellow line is temporary. And so what I need are the Newton's third law pair forces at point P. So I've got, some of the forces here, and I need their little partners in crime on the other side. And I'm going to choose just to work in vertical components. So a 5 pound upward, that one becomes 5 pounds downward. And a square root of 3 root 5 rightward becomes a square root of 3 root 5 leftward. Okay, so I've got my my Newton's third law pair forces there, and so I'm done with that free body diagram. Now I can focus on these, and I should have turned my line of symmetry on. So to fix that, I'm just going to remove this one. Okay, and we'll just continue to work over here. All right, let us crunch through this. So I've got two unknown forces. I don't have anything at weird angles, so man, super easy. Let's just do a summation of forces. in the y direction equals 0. And so I've got 5 and 10 down and an unknown up. So therefore, N sub Q equals 15 pounds pushing up. Oh, hi there. Sorry, my cat just came up. I forgot I was being recorded. Oh, that's hilarious. Okay, I'll try to field off the cat and finish the problem. So the next piece, summation of forces in the x direction equals 0. And so now all I need to do is match these two forces. So N sub m equals, sorry, I got thrown off my game with the entrance of my cat. Okay, N sub m is equal to square root of 3 times 5 pounds, and we're in final answer mode, so I'll go ahead and punch this through the calculator. So 3 square root equals times 5 equals 8.66, which I should have been able to do that in my head, but that's okay. All right, 8.66 pounds. And the direction of that force is rightward. Okay, so those are your final answers, N sub Q and N sub M. Thanks for watching.